So the next module is on orthogonality. We've seen this before. Orthogonality is simply related to the idea of two vectors being perpendicular to each other. You say two vectors x and y are orthogonal if their standard inner product is 0. Okay, this we've seen before. This is my x, this is my y. This will give me, if I take the inner product between these two, it will give me 0. Okay. We know this for a pair of vectors, right? Now imagine you had a set V of vectors. And where each Vi is a member from Rn, is an n vector. Okay. You say that this set is a set of orthogonal vectors if Vi transpose Vj equals 0 for all I equal j. Okay. We of course assume that there is no 0 element here. Okay, and maybe we can say that by saying if these two conditions are satisfied, then you say this is an orthogonal set of vectors. Okay. What I should simply say is strictly greater than 0. But if Vi transpose with itself is equal to 1, then you say this set is not just an orthogonal set of vectors, you say it's an orthonormal set of vectors. Okay. It simply means every vector is perpendicular to everything else, and each vector has length 1. What is not a subspace? Subspace. What is a subspace? Yeah, set of vectors from a vector space, and the subset itself forms another vector space. Then it's a subspace of something, right? Let's say we have two subspaces, S1 and S2, and these are subspaces of Rn. Okay. This idea of, well, we've talked about vectors being orthogonal. It turns out you can talk about two subspaces being orthogonal to each other. Okay, you can say S1 perpendicular to S2, which simply means S1 is orthogonal to S2. The subspace S1 is orthogonal to S2. And in fact, here we will often write X perpendicular Y. This means the vector X is perpendicular to vector Y. Okay. We can extend that idea to subspaces and say an entire subspace is orthogonal to another subspace if x1 transpose or x transpose y is 0, where x is from S1 or for all x from S1. Okay. If you say two subspaces are orthogonal to each other if you take any vector from S1 and any vector from S2 and you take their inner product, it has to come out to 0. And this applies for everything. It doesn't matter which ones you choose. No matter you choose anything here, no matter what you choose here, the inner product will always be 0. That means it's always perpendicular. Right? For example, an example like this. If you're talking about R2, say this is S1. This is S2. Both of these are subspaces of R2. Okay. Well, let's say the direction between the angle between these two lines is actually 90 degrees. Okay. Then you would say these two subspaces are orthogonal to each other. Okay. But if you consider a third subspace, this is S3. S3 is not orthogonal to either of those subspaces. S3 is not orthogonal to S1. S2 is not orthogonal to S3. Okay. Whereas S1 and S2 are orthogonal to each other. What about 3D? Say we had R3, right? Okay. This is X1, X2, X3. Is the X1, X2 plane a subspace of R3? The plane containing X1 and X2. Is there a subspace of R3? Well, it's a flat surface with the origin in it. It's a subspace. Okay. What about the subspace X1, X3? The vertical plane and this plane that's supposed to be coming. Well, maybe let's. So this is X1, X2. Let's say this is X1, X3 plane that's coming out of the board. So those two are subspaces. This is a subspace. This is a subspace. The origin is here. Are these two subspaces orthogonal to each other? What do you think? Well, if they are orthogonal to each other, then no matter what vectors you choose from this plane or this plane, they should be perpendicular to each other. Are there cases where that's not true? Well, the line x1 is in both the subspaces. If I choose two vectors to be from x1, they will not be orthogonal to each other. Yeah, here. This plane, right? This line, see these two intersect in this line, no? If I choose two vectors along that line, you can say one of them belongs to this plane, the other one belongs to this plane. Their inner product is not zero. So in this case, the intersection of two planes in X3, R3 do not, I mean, two planes do not form orthogonal subspaces. But if you take this plane, X1, X2 plane, and the X3 line, right? These two subspaces are orthogonal to each other because no matter what vector I choose here, it's always perpendicular to this vector. Okay. Yeah. So that's essentially the idea. Okay. And one thing you'll notice is if two subspaces are orthogonal to each other, an implication of this, right, is S1 intersection S2 should only have the zero element. If you consider the X1, X2 plane and X1, X3 plane, their intersection is not zero. Their intersection is the X1 line because X1 is there in both of them, X1, X2, X1, X3. Okay. Whereas if you consider the X1, X2 plane and X3, the only place where they intersect is the origin. So okay, and you can see that here as well. S1 and S2 intersect only at the origin. So if you take the intersection of these two sets, you only get zero. Okay, but here is the other issue. Yeah, if the two sets are orthogonal, then this is true. Okay, but if this is true, it does not imply they are orthogonal. Okay, because here S1 and S3, the intersection of these two is still only zero, but they are not orthogonal to each other. Okay? So this implies that does not imply this. Okay, so one way to quickly verify is you see if this is true. If this is true, the two sets can be orthogonal, two subspaces can be orthogonal, but you will have to verify that. If it's not true, right? If the intersection is more than the zero vector, then for sure they are not orthogonal. It's the same idea as whether zero is present in a subset in a set. If it's present, it can be a vector space. If it's not present, you're done. It's not a vector space. Okay, the same idea. Another concept that we look at is this idea of complementary subspaces. Okay. Okay. Let's say S1 and S2 are subspaces of Rn, some parent space. Okay. We say the two subspaces are complementary subspaces if two conditions are satisfied. S1 intersection S2 is it's only the zero vector. Okay. The only thing that is common between them is the zero vector. And if you add the two subspaces, you get your entire parent space. What is the definition of addition of two subspaces? Maybe go back to your sheet. What does it mean? What happens? I mean, what do you get when you add two subspaces? I don't know if it's there in the sheets. Yeah. No, no. The resulting set is a subspace, but what is the definition of how do you generate this sum of these two subspaces? What is the definition of or what did we say this addition means? Yeah. Yes. This is simply a set of all elements such that you take uh, well, let me put it like this. It's the set like this. It's the set of sum of two vectors where x comes from S1, S2. You simply take all possible pairs of vectors from S1 and S2 and you add them all together and then you form a set. That is the sum of, that's essentially the sum of these two subspaces, right? And you say that the two subspaces are complementary if their intersection is zero. And if you add the two subspaces, they cover the entire parent space. Okay, here S1 and S2, are they complementary subspaces? Well, the intersection is zero. Okay, if you add these two subspaces, do you get all of R2? Well, adding these two simply means taking any vector from here, taking any vector from here, and adding them together, you get a point. So you can, if you choose any elements from S1 and any element from S2, and you add them, you will in fact get all of R2. Right? So in this case, S1 and S2 are complementary subspaces. What about S1 and S3? Complementary again, right? With vectors along this direction and vectors along this direction, I can generate any point. Right? All I would have to do if I want to generate this point, I simply draw a line parallel to this line and see where it meets S3. And then I draw a line parallel to S3 until it meets S1. If I add this vector from S3 and this vector from S1, I'll get this vector. You can do the same thing. Something here, you do the same thing. And then here you extend this. If you add these two vectors, you'll get this one. So you can get every point, right? So S1 and S3 are orthogonal, not orthogonal, they're complementary subspaces. What about the set S1 itself? Well, the idea does not apply because there is only one. To talk about complementary subspaces, you have to have two. But maybe I take another example. In R3, let's say we consider two subspaces, S1, the X1, X2 plane, and X1, X3 plane. Do they form complementary subspaces? Okay. In R3, right? Let's say we consider the X1, X2 plane, the plane that contains the X1 axis and the X2 axis. You consider another, let's say that's the S1 subspace, X1, X2 plane. We consider another subspace, which is the x1, x3 plane. It means x3 is this line, so that's this plane. So so S1 is this, S2 is this. These two are subspaces of R3. Now the question is, do they form complementary subspaces? What do you think? Okay, why? Hey, is it zero? Okay, if you take this plane, right, and this plane, is the intersection between these two planes the zero vector? Really? No. Here. Here, this is your x1, x2 plane. This is your x1, x3 plane. The intersection is not zero, right? The intersection is this line. They meet at this line. So it's not just the zero vector. Right? So the first condition is out. That means they are not complementary subspace. But what about the second one? Is the second one true? If you take any vector from this plane and any vector from this plane, if you add them together, can you get all points in R3? You can, right? If I want to reach this point, I can find a vector in this plane and I can find a vector in this plane such that if I add them together, I'll get this point. Okay. So in this case, for these two subspaces from R3, the second condition is satisfied. The sum of the two subspaces is in fact R3, but they are not, their intersection is not zero, so they are not complementary subspaces. Okay. But this is, if S2 was just the x3 line, basically this line, if you want to get to this point, you simply find a vector in the S1 plane, and you find a corresponding vector along x3, and if you add them together, you'll get this point. Similarly here, any point, you can get any point you want. And these two, so you have the plane, you have the line, they only intersect at this point. The intersection is zero, so these two form complementary subspaces. Okay. In fact, if you have complementary subspaces and S1 is perpendicular to S2, then you say S1 and S2 are orthogonal complements. Okay. The two of them together not only span your entire parent space, they are also perpendicular to each other. Okay. See, what will happen is, or this idea of the intersection being zero and the two of them getting all of the parent space is kind of connected to this idea of linear independence. Okay. In linear independence, all you're saying is information contained in one vector is not contained in anything else, or this vector contains information that is not present in any of the other vectors in a set. This idea of the intersection being zero is similar. There is information in S2 that is not present in S1, it's vice versa. And together, they give you all information. Right? If you have two subspaces that are not complementary subspaces, okay, but they still span your entire parent space, it simply means that there are multiple ways in which you can represent a vector from Rn using vectors from S1 and S2. Okay, maybe that's confusing, but I'll clarify that. If you have complementary subspaces, right? If you have S1 and S2, these are complementary subspaces. Okay, and let's say so complementary subspaces of Rn. That means if you sum them together, you get Rn, and they don't share anything in common except for the zero vector. Then, if you have a vector v that belongs to Rn, okay, and you have two complementary subspaces like this, it turns out you can write v like this. Okay, as a sum of two vectors. v1 and v2, of course, are from Rn. but V1 is from S1 and this is from S2. This vector comes from subspace 1. This vector comes from subspace 2. And this is the only combination of two vectors that will give me V if S1 and S2 are complementary subspaces. Okay, that means if I have complementary subspaces, I can represent any vector in Rn using using a vector from S1, using a vector from S2, and these are the only two vectors that will give me V. If I change any one of those, I don't get V anymore, I get something else. Okay, but if you don't have complementary subspaces, for example, this is true, that means the two subspaces together can generate all of Rn, but this is not satisfied. It turns out that then this combination is not unique, right? There are infinitely many V1 and V2 that could have produced this vector. And you should see the connection between linear independence and a unique representation of a vector. But if you have a linearly dependent set that still spans your entire vector space, then the representation is not unique, right? The idea is similar. Except there we were dealing with a set of vectors. Here we are dealing with a set of subspaces. Okay. In fact, this idea of complementary subspaces is not restricted to just two subspaces. You can have k subspaces, and we say these are complementary subspaces if Si intersection Sj is only the zero vector when I is of course not equal to j. Okay, and if you add all of these together, you get Rn. Okay, together they generate the full parent space, and they all share only the zero vector, nothing else. Right? Then, if this is the case, then if you choose any vector from Rn, V, you can write it as the sum of k vectors, right? Each of those vectors coming from these k subspaces, V1 plus V2, Vk, and this is unique. Okay, there is no other set of vectors V1 to Vk that will give me V if this is true. Okay, and these vectors, right? These are called the components. This is called the component of V in S1 or along S1, which simply means this is the vector from S1 that you need to choose if you want to generate V and add it to something else to generate V. Okay. Just one last item about this. If you have complementary subspaces, then you can write it like this uniquely. What happens if S1 and S2 are orthogonal complements? They're not just complementary subspaces. S1 is orthogonal to S2 and they span Rn. If that is the case, what can you say about V1 and V2? Sorry? Yes. If S1 and S2 are orthogonal complements, then V1 transpose V2 is 0. That's all. That means the component of V in the subspace S1 will be perpendicular to the component of V in the subspace S2. And if, in fact, if these are orthogonal complements, each of these VI's will be orthogonal to the other one. Okay? All right. I'm going to stop here. We will complete this tomorrow. But if there are any questions about what we've discussed so far, yeah, we can talk about it now. And please make sure you revise this. We'll try and upload the video by today. Please revise this before tomorrow's. Yeah. Oh, sorry. I think we have about 10 minutes. I thought it was already 9. We'll continue. Okay. We'll leave this for now, right? This is all I wanted to say about subspaces and complementary subspaces and orthogonal complexes. We'll now move to another very important idea on projections. In fact, orthogonal projection. Let's start with R2. Say we have a subspace in R2. Okay. And this subspace is spanned by this vector A. And this subspace, I call this SA, and this is simply the span of the set. Okay. Now, let's say I have another vector. B. Okay, that does not lie any arbitrary vector B. Okay. The orthogonal projection of this vector. So you can orthogonally project a vector onto a subspace. Okay. So you can, in fact, project a vector onto a subspace. Okay. There is an operation called projecting a vector onto a subspace. Okay. And in fact, in this particular lecture, we'll only look at not just any projection, we'll only look at orthogonal. We can orthogonally project a vector onto a subspace. And that simply means this. You go to the tip of the vector and then you draw a line. Okay. You draw a line such that it meets the subspace like this. And that line is perpendicular to the subspace. Okay. You find out where that line meets the subspace. Okay. And then you draw a vector from the origin to where the perpendicular line meets the subspace. Right? And this vector now is this vector is, we call it BSA, or for now say BA. Right? We call this vector the orthogonal projection of B onto the subspace spanned by A, or onto the subspace SA. Okay. I hope geometrically at least the definition of what is an orthogonal projection clear, at least in this particular case, where you are projecting a vector onto a one-dimensional subspace. How would we find out B? If you knew A and B, how can we find out this BA? Sorry, how can we find out BA if we know B and A? Yeah. Sorry. Theta, is it? You get the theta? Okay, all right. So you're saying let's find out this angle. Okay. And then you do what? You're right. You're almost in the right direction. So you find out theta. Okay. Okay, all right. So you're saying let's do Let's say this angle is theta. Okay. And you're saying cos theta is what? Hey, hold on. Okay. Sure. Let's use linear algebra and not go back to 600 trigonometry. You're right. We can do it that way. But let's, yes. Not x transpose y in this case. Transpose v. Is that enough? Sorry? Yeah, you have to divide it. By what? Great. Fine. Now what? Sorry? How do we find out BA? This vector. What we want to find out is BA, the orthogonal projection of B onto A, onto the subspace spanned by A. So we've got cos theta. That's all we have. Now what do we do? See, why did we want to get cos theta in the first place? It's correct. I mean, your approach is right. So what next? There's probably a reason why you wanted cos theta. Yeah. Theta will be some value. Okay. Let's say we found that out. Now what do we do? I want a precise expression for this BA, which is the orthogonal projection of. Wait, let's make it simple. Let's just call this as BS. Yeah. So you have theta. In fact, we have cos theta. In fact, if you just do this, if you know A and B, if you compute this, you get cos theta. You don't even have to worry about getting theta. How do we get this? Yes, that's correct. What is this length? What is this? So you take this and you multiply this by what? The length of B, right? Yep. Maybe go back to trigonometry. What is this? If you know the hypotenuse, what is this? This theta. What is the length of the adjacent side? H cos theta, right? Okay, all right. What is the hypotenuse here? Okay, so it looks like now we can get this length, right? This distance, the distance between this point and this point is what? What is this? You say B cos theta. Great. But what is cos theta? Cos theta is this. That means this length is A transpose B divided by A B. But you've multiplied cos theta by B. So, in fact, the length is just this. Right? B cos theta will essentially give you this. But this is just a single number. But we want this vector BS. How are BS and the vector A related? Yes. What is the scale? Scale. Yes, that's all. It's simply this number 8 transpose B. This will be okay. We run out of time. Just note this down and then see. I want you to do this numerically and then see if this gives you the right expression that we want. Okay. Let's put some numbers to this. Let's say A is okay. Okay. Sorry, what? Hi. Sorry, yes, you're right. That's what you meant, right? Yeah. And let's say you try this A first and see what you get. I mean, you can draw this on a graph sheet and then do this geometric procedure and then find out what this BS should be using this A and this B. And then you try this. And you do the same thing using this A and this B. Okay. And you apply this approach to find BS. And then you tell me your the answers to these two tomorrow. Yeah. And then we'll take the rest of the discussion from that point on. Okay. All right. We stop here now.